Hey guys, here are notes for 7.5, coordinate proof. And here's a starting. Two vectors are represented by vector u and vector v. So here's vector v here. Vector u is this bottom one from initial point P to terminal point Q. And it says the components of u, so the components of this vector are a0. So you're going over a and up 0. That's the components. The components of vector v are over b and up c, Find the components of the result of the vector as a result of when you add these two together. Vector r will be the result of adding vector v plus vector u. So here's vector r when you add these two together. So you're adding your two a plus b together, you're adding your c plus 0 together. Now you might be able to see a couple pieces here. This is length b right here. Over b and up c would be this point right here. So this is length, that's b. So if I was to bring this over here, we're trying to see how we're getting to point r. We would go up c units. So over b units, up c units would get us to the point of a, which is this bottom piece a, plus b, because this was the point a0, so this from here to here was a, then that's plus b, and then you go up c, so a plus b comma c. And basically what you would have made here would have been a parallelogram. You can kind of see the parallelogram there. When the result of the two vectors added together would have made a diagonal of this parallelogram. So that's a little bit just on the coordinates. We did a little bit of this on our starters already. Find all the coordinates of the vertices of each polygon. So we want to find the rest of these points. So if this is a square, and this is over a and up 0, that means all of these sides are a length. They're all a length of a. So this would be over 0 and up a. So over 0, up a. This would be over a and up a. So this would just be the point AA. This is a perfect square here. They're all a's. This is an equilateral triangle, and from O to this point right here is over A and up 0. So this length is A. So this length, if it's equilateral, has to be negative A, because you're going negative direction. Negative A and up 0. So this would be negative A0. Now, the altitude of an equilateral triangle, I don't know if you remember this, but this little right triangle has to be a 30 degree, 60 degree, 90 degree right triangle, because the equilateral triangle has all 60 degree angles, and you cut the 60 degree angle in half and made two 30 degree angles in here. So basically what we would have then is a 30 degree angle. Degrees there. We'd have our 60 degrees here. Just right in that angle. And then of course this one is our right angle right here. So you'd have a 30, 60, 90 right triangle. Let's make this a little smaller. That's better. And the short leg is A. So if the short leg is A, the long leg has to be A times radical 3. So you're going to go over 0 and you're going to go up A radical 3. So that would be this point right up here for point Y. This is a parallelogram. You might remember it from this page right here. We had another parallelogram. So we added the A plus the B, and then it was up C. So we've probably got the same thing here. We've got our length of B right here. That length of B is going to be the same over here. And so it's going to be the A plus the B, and then up C units. So A plus B, and then comma C. So those are all the vertices of each figure. All right, moving on. Use a coordinate plane to prove that the diagonals of a rectangle are congruent. So we want to prove that this diagonal OB is congruent to this diagonal CA, the diagonal CA. So first off, they're telling us that it is a rectangle. So that's a given statement. So it says prove that the diagonals of a rectangle are congruent. So we know it's a rectangle. Secondly, in a rectangle, angles A, B, C, and O are right angles. Because of the word rectangle that they give you here, it's going to be a definition of a rectangle. Usually whenever they give you a keyword, you're going to have a definition of that keyword next. So because it's a rectangle, they have to be right angles. Now that means that a squared plus b squared equals ac squared. So here's ac right here, and you got your a squared plus your b squared. That's a right triangle. Because of the right angles, we have a right triangle, and therefore a squared plus b squared would equal ac squared. And I think I forgot to put squared on this right here. I don't know if I can edit that or not. I think... No, I didn't forget. What I forgot to do, and you guys will have to bear with me here, I forgot to put in a square root sign right here. So that's what it should have been. AC is the square root of a squared plus b squared, and that's Pythagorean theorem, and it's the same thing here. So let me double duplicate this. That's not what we want to do, so let me get rid of that for a second. Let's put this one. I don't want that. Okay, so we want that. Now we want to put this here. Okay, then for number 5, AC equals OB. These two have to equal each other because these two are exactly the same. So that's just going to be substitution. And that proves that the two diagonals are equal to each other. So there's a proof. Let's go to the next one. Another proof. Prove that the length of the mid-segment of a trapezoid is the average of the two bases. So we've got a bunch of numbers in here, right? And we know where our mid-segments are. So let's start. We've got the midpoint of AD is the point 24. So if I go over 2 and up 4, that's the midpoint. The midpoint of CB is over 13 and up 4. So 13 over and up 4, that would be the midpoint of CB. And that would be, let's see what that is. That's just going to be, oh man, did it again. Let's see if I can get it to come now. Okay, that's just midpoint formula, that's all that is. Midpoint formula. Because all we did was add the x's together and divide by 2, add the y's together and divide by 2. That's your midpoint formula. So that's how I found the midpoint of these two sides. Now, the length between the midpoints is 11. So if you count over this much, you would get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 units. That would be the distance formula. Actually, we could have used distance formula too, but when it's a horizontal line, you can just count. But if I had used the distance formula for these 2 points, I would have gotten 11. So distance formula works, and the just counting works here. The length of DC equals 8. So I can count here 1, 2, 3, 4, 5, 6, 7, 8 again, or I can use the distance formula again. The length of AB is 14. So if I count of these, it's going to be 14. The average of these two bases is 8 plus 14 over 2, which is 11. That is just using the average of two numbers formula. You know, when you average two numbers, you add them together and divide by 2. And then the mid-segment equals the average of the bases. The mid-segment is 11. And then the average is 11. So that's just 11 equaling 11. So the mid-segment is the average of the two bases. We just proved that this middle segment is the average of those two bases. Okay, coordinates in space, three-dimensional figures. So you've got an x-axis, a y-axis, and a z-axis. And you can see they're three-dimensional figures. So you probably know the point in here would be 0, 0. Now it's going to be 0, 0, 0 because you're going 0 on the x-axis, 0 on the y-axis, and 0 on the z-axis. This point right up here would be 0, 3, 0. Over 0, up 3, and over 0. So 0, 3, 0. This point right here would be over 7, up 3, and 0, not anywhere else. 7, 3, 0. This one would be 7, 0, 0, over 7, up 0, over 0. This point right here would be over 0 first, 0 on the x-axis, 3 on the y-axis, and 7 on the z-axis. So 0, 3, 7, over 0, up 3, over 7. And then this one right here would be over 0, up 0, and over 7. So that'd be 0, 0, 7. This point down here would be 707. It means you go over 7, you go up 0, and then you go over 7 again. So 707. And this one right here would be 737. You'd start at your origin, you'd go over 7, you'd go up 3, and you'd go over 7. And that would be your point right there. So those are three-dimensional coordinates, x, y, and z. That's what the coordinates would look like. So let's list points C, E, F, and G. So point C, let's see, I'm going to go over 15 on the x. I'm going to go up 8 on the y, even though it looks like 3, but this is an 8 and this is a 15. They gave us the numbers to use. So over 15, up 8, and then over 0. So I'm thinking it's going to be 15, 8, 0. And that is right, 15, 8, 0 for C. Point G, you would go over 15, up 8, and then over 5. This is 5 units on the z-axis, so this is also 5 units. So 15, 8, 5 is what that one's going to be. That one's the right one, G right down there. 15, 8, 5. F and E. Let's do E next. So it's 0 on the x, it's 0 on the y, and it's just 5. 0, 0, 5. And the F is going to be 0 on the x, 8 on the y, and 5 on the z. 0, 8, 5. So those are your coordinates for the missing points on that three-dimensional figure. And the last slide is going to be the distance formula in space. So if you've got a three-dimensional object, and you've got, like, say you want to find the length of this diagonal from this bottom corner of the box to this top corner of the box, and you've got the 2 points, you can apply the distance formula where you're just adding in the z coordinates. This is the same distance formula we already have. This is just adding in the z coordinates. So this one right here would be where it starts, x minus x. So it's going to be 6 minus 0, y minus y, so that's going to be 3 minus 0, and z minus z, that's going to be 0 minus 5. So you're going to get 36, and you're going to get 9, and you're going to get 25, and then which is square root of 70, which is going to be about 8.37. So this is about 8.37 units long. So we can still apply the distance formula in space. We're just adding the third coordinate. That's all it is. All right, there's your 7.5 notes.